Okay, so we're continuing in chapter 4 to discuss how we solve the Schrodinger equation in higher dimensions. We've done a lot in 1 dimension. Homework last time, or do for today, was to do the particle in the cube, 3 dimensions. We're headed towards doing the electron from the proton, the hydrogen. So we don't want to use Cartesian coordinate system. Cartesian coordinate system is not convenient. In principle, you could do it, but it's hard to solve something like the hydrogen atom using a Cartesian coordinate system. So you want to pick a coordinate system which conforms to the symmetry of the problem. And the symmetry of the problem with the hydrogen atom is that the electron is moving in a potential that goes like 1 over distance from the Schrodinger, from the center, from the proton. And so it's more natural to use a spherical coordinate system because that system has spherical symmetry. If you think of the electron moving in some kind of potential, the potential has spherical symmetry. So just looking at potential in the Schrodinger equation, the potential is just 1 over distance. It's the negative of it's the charge of the proton times the charge on the electron divided by R. So it's a spherically symmetric problem. So potential is spherically symmetric, which means that if you close your eyes, I'm going to rotate the system about some axis by some arbitrary amount. You open your eyes, you can't tell that it's been rotated. Potential hasn't changed. So it's more natural to use, and mathematically much more convenient to use a coordinate system which conforms to that symmetry. So it's rather than jumping to 3 dimensions, I want to start first in 2 dimensions. Just sketch out some aspects of a particle in a circle. So we did a particle in the square. What if we did a particle in the circle? So it's confined to be in the circle. I'm not going to do the whole detail here. I just want to show you another step towards 3 dimensions. And we did the particle, when we did the particle in the square, it was natural to use coordinates, Cartesian coordinates, because the potential itself has that kind of square symmetry to it. But now, when we put the particle in a circle, the Cartesian coordinate system would not be very convenient. And so I wrote the wave function as a function of x and y. And then when you did the cube, it's natural to continue to use the Cartesian coordinate system. All right, but now let's look at the problem of the particle in a circle. So it's confined to be inside of this circle. So the potential is infinite out here. Wave function has to be somewhere inside. Let's say that the radius of the circle is a. So that Cartesian coordinates would not be an obvious choice in this case. What would be a more natural looking choice of coordinates? Ones that we covered earlier. Polar coordinates. So in the polar coordinate system, you have 2 variables rather than x and y. You describe a point inside of the circle. That's in terms of r and theta. And we had this, went through this exercise of how to convert from Cartesian to polar, and then the other way around. X is equal to r cosine theta, y is equal to r sine theta. So the Cartesian, the Laplacian operator comes into the Schrodinger equation when we calculate the kinetic energy. The operator is related to the kinetic energy. In Cartesian coordinates, it looks like this. In polar coordinates, it looks like this. Okay, so now we want to write the Schrodinger equation and solve it in the polar coordinate system for this problem. Like I said, I'm not going to go all the way through this. Well, obviously, we're going to express the wave function in polar coordinates, so rather than in terms of x and y, it's in terms of r and theta. And now, for instance, we have the time independent proving equation for the particle in the box. It looks like this. And we also have the condition. The wave function vanishes on the circle, on the outer perimeter of this region. Okay, and then once again, we would, it will work to try the separation of variables. So we would write wave function as a product. Two functions, one each of r and theta. So we'll try separation of variables. And this problem of the particle inside of a circle does nicely separate. And so you'll get one equation for the radial component and one equation for the angle. I don't want to go through all of this right now, but I will show you what the result is for the angle. Yes, sir.
For that psi of A of theta or A and theta, is that potential or is that the equals zero? Is that potential or is that just
The wave function has to vanish on the, it's a boundary condition. The wave function has to vanish on the perimeter, just like it did in the square and the cube.
oh,
Yeah. So regardless of the angle, the radius is A, the wave function must vanish.
all right.
In terms of these separated coordinates, it means that R must be 0 when evaluated at A, and that will accomplish the boundary condition. So I don't want to go through all of this, but it's basically the same idea I showed you before, except that this operator is now a little different than what we were dealing with before. So I don't want to look at the radial part, but let's just look for a moment at the angular part. So you get, when you do the separation of variables, so this symbol here that I'm writing is like a capital theta. I'm trying to write a capital theta. It's a function of the angle theta. Okay, so that's this constant here is the separation constant. So when I plug this into here and then collect terms in theta and r, I get two different equations. One that depends only on r. One side depends only on r, the other side depends only on theta. And I use the same trick that we did before. There's a separation constant. And then looking at the theta equation, you get this. And for the r equation, there's another equation, which I'm not going to go through. It's a little bit complicated. But this one is quite simple. You should, by now, just recognize that anytime I have blob second derivative of some variable equals some constant times blob of that variable. Doesn't matter what blob is, and it doesn't matter what the constant is. What is that equation? That goes back to the one that you started in mechanics. Simple harmonic oscillator. Okay, and so we have, depending on the sign of that constant, these are real or complex exponentials. All right, the second derivative of a function, let's look at this. The second derivative of this function is either going to be real or a real exponential or a complex exponential. Okay, now this brings up a subtle question about the wave function. Because if it's a real exponential, let's say there's some constant like that. Suppose it looks like that would be as real. Then we start here with theta equals to 0. If we go around, consider how the wave function is changing. You go around the circle, it comes back to this point. It should have the same value. Now this is an interesting argument, and he goes into it into some depth in the text. We're not going to cover that. What kind of condition is there on the wave function here? And I'm going to refer you to the details in the textbook that we're not reading, if you're interested to understand. But the idea is then that if I go too high around, the wave function doesn't match itself. If b is a real constant, there will be a discontinuity in the wave function. If it starts off at theta equals to 0, so the wave function would be 1. Comes around here, now it's going to be e to the b2 theta, which is not going to equal itself. So there would be a discontinuity in the wave function. We've said in principle that the wave function should be continuous in first derivatives. So a real value of b is not going to work. And that real value of b would correspond to this constant, but b squared is the constant. So if b constant is positive, b would be real. We don't have a solution. Shouldn't be a solution to the Schrodinger. Let's suppose this constant is negative. So this would be if the constant is positive. Let's suppose that the constant is negative. What kind of solutions do we have then?
Complex or sine cosine.
That's right. Going to write it like this. So now we take the second derivative of this, we get a negative b squared, so the constant would be negative. Okay, let's add 2 pi to the angle. So let's look at theta equals to 0, the wave function, the theta part of the wave function would just be 1. If we go all the way around the circle, we come back to a value of e to the I b2 pi. That matches only if there are certain particular values for b. What would those be? Values for b would be we want this to equal 1. 0 is one of the allowed solutions, but there are more.
One over
b n pi x,
2
just
pi
like
on 1.
Yeah,
cardboard box.
that's right. It's a multiple. It has to be an integer multiple of 2 pi. So e has to be an integer. So we find out that these are the allowed solutions where m is equal to any positive, any integer, positive or negative. As long as it's an integer, the wave function will come back around and match itself on the other side. So in other words, we have a quantum number here, which can be any integer. So once again, we're encountering quantum numbers. We had a quantum number when we put the particle in a box. We had a quantum number associated with confinement in the box. We had a simple harmonic oscillator. We had a quantum number, which corresponded to confinement inside this potential well. So for every direction like this, we're getting a quantum number. So there's a quantum number associated with the angular descendants. And that quantum number is related to the separation constant. So we find out that that separation constant has to be the negative square of an integer. Negative integer squared, that's separation constant. The only way we can get a solution. All right, then when we go back to solve the radial equation, that quantum number is going to come back in, and I don't want to go through all of that. The separation variable shows up in the other part. I don't want to go through all of that, but I just wanted to show you this. This is a very interesting result. And we're going to see it play out again in the hydrogen atom. Part of the equation, part of the solution in the hydrogen atom is going to look like this. Okay, so if you look at this, let's look at the real parts. terms that look like this. We have functions that look like this, and the imaginary part is like this. So these are pieces of this. Functions like this will come into this part. And these are periodic. If you go 2 pi around, they return to themselves. If you go 2 pi around, it goes on 4 pi, goes on 6 pi, goes on 8 pi. So it comes back to itself. Okay, so then we could look at these functions. You could plot them on a circle, and which is kind of awkward, right? If you plot them like this. I'm plotting, say, the real part of this function. It has to come back around and back to itself. That's a resonant condition. Remember when we were talking about the Bohr quantization condition was like a resonant condition. It has to go around and match itself. This is showing up in like that Bohr quantization condition. But it's coming out as a natural result of the Schrodinger equation, not something that's imposed separate. So this is contained within the Schrodinger equation and the condition that we said the wave function has to match. Now this is a subtle argument. I don't want to mislead you that this condition is quite as simple as I just stated. There's some subtleties involved in this, and I don't want to go into it at this level. Go into the subject, say at the senior level, that should be covered carefully there. It's just for an introductory course, we're not going to worry about it. Just plan it in your head. Not quite as simple as I just painted. Okay. There is a subtlety, it's an important subtlety. Okay. So, okay so far? All right. Well, I'll give you a hint of the subtlety. The wave function, well, no, let's leave it at that. I'm just going to leave it at that. I was tempted, but I'm going to. Okay, so that's a brief sketch of one part of the particle in a circle. Just the angular part, not the radial part, but the angular part. But you can see how to go to do the radial part next. That gets into decimal functions. Really want to go into that now at this level. But we have this condition that we have to match. So this puts a condition on the energies. Again, we have a discrete spectrum of energy levels for the particle inside of a circle. Okay. So now let's go to 3 dimensions. So we want to write this Laplacian in 3 dimensions, but first we need to define the coordinate system. We haven't talked about spherical coordinates. We're going to use spherical coordinate system. I'm going to project this. There's a diagram like this that I put into the homework. This is from diagram comes from mechanics textbook, but this is a very common coordinate system. Let's see if I can.
Are we still doing the particle? So like a particle in a sphere?
You could do a particle in a sphere. Yeah, that would be a problem we could do with the spherical coordinates. Okay, so now we see the Cartesian coordinates x, y, and z. We have spherical coordinates. We have a distance. We have 2 angles we have to specify. So if you want to specify the position on the circle, say, you need 2 angles. On the Earth, we use latitude and longitude, which amounts to 2 angles. So one of the angles is the angle from the North Pole. So let's suppose we put Z along the North Pole. The angle that's made with the North Pole, that is the Z-axis, that angle is called theta, which would correspond to which, longitude or latitude? Or do you remember the difference between them? This is latitude this way. Oh man. Latitude is easy to determine. How can you find your own latitude? Easy at night. It's clear. How do you find
Cell phone.
what was that?
A cell phone.
A cell phone. What if you don't have a cell phone?
And I'm screwed.
What's that? North Star. Polaris, North Star. So if you know the angle of the North Star above the horizon, you can determine your latitude from that. Because if standing on the North Pole, the pole star is very close overhead. Does a little bit of circling, but not much. So the angle that it makes will give you your latitude. Okay. Longitude is much harder to measure on the Earth. Like you're out on the ocean sailing, you want to determine your position. You can do it with longitude only if you have a really good clock. It's synced with say a reference clock in England, for example, Greenwich Mean Time. So the longitude is this angle theta. So the way you get that is you project that into the XY plane, and then this angle phi, this angle phi is now our polar coordinate, like what we did before. So it's a combination. So it's polar coordinates like in the XY plane, but now we've got an extra angle here. So let me write down the coordinates for you. This is in your homework, so you'll be able to study it some more. I think I want to erase that. So I wanted to show you the figure because I didn't know if I was going to be able to be good enough at drawing that on the board for you. So we have now in 3 dimensions, we have one possibility is Cartesian coordinate system, spherical coordinate system, and they relate to each other following way. Then let's see. The cosine of theta is equal to c squared of x squared plus y squared plus r squared. And then the tangent of phi is 1 over x. So that's how you go from x to r and theta and phi. The other way around, let's see, x, y, and z is equal to r cosine theta. How you go from polar to Cartesian. So it's kind of similar to the 2-dimensional polar coordinates, a little bit different. It resembles the polar in the XY plane, but there's this third direction, third dimension, which involves the angle theta. Okay, so then I'm just going to write down the result for you to figure out the Laplacian. A little work, but it's in the back of the book. There's an appendix at the back, appendix 5, that has the Laplacian and different coordinates. Not real tidy. Okay. And this is in the back of the book, so you need to look it up. And he also writes it down in the text. So the details are not important. I'm not wanting you to absorb all the details of the spherical coordinates at this point. It's okay if you want to study it, but I'm not asking that you study this in detail. But you can see that we have these derivatives with respect to r, derivatives with respect to phi, derivatives with respect to theta. Similar structure to what we had before, a little bit different. But again, what we're going to do is we're going to solve the time independent Schrodinger equation. Let's suppose we wanted to do a particle in a sphere. We want to solve this equation now. We want to find the pure modes for a particle confined to a spherical. The cube, it was naturally used coordinate systems. For the particle in the sphere, we want to use spherical coordinates. Okay, so you have this, and then what's the next thing to try? here. Separation of variables. For the particle in the sphere or for the hydrogen atom, it makes a very nice coordinate system to solve this differential equation. Using separation of variables is right here. Okay, now this angle theta, by the way, does not correspond to the angle theta that was used in the polar coordinates. The one that matches more closely is the phi. This is the angle in the xy plane. So the polar coordinates, there's been a change of name for the variable. So phi is the one that's in the plane. Okay, substitute this in. You get separation constants. Go through this whole procedure again. Get, instead of one differential equation in three variables, you get three equations, each in one variable. Get one equation for r, one for theta, and one for phi. Here's the phi equation. Here it is again. Same equation. Simple harmonic oscillator shows up in a lot of ways. Okay. Same condition applied if we apply the condition that the wave function meets itself on the other side around. This constant has to be negative. It has to be the negative square of an integer. So it has to be constant is equal to negative n squared, where n is in the integer. Get these. That much is the same, but now we have the other angle. And that part, I'm just going to summarize what happens here. Okay, so he'll lay out for you in the book the solutions, but he won't derive them for you. At the senior level, you would go through the derivation of the theta part, as well as the radial part. That will be in the course that you take as a senior level quantum. We'll actually go through the technique of solving these differential equations and show all the pieces to them. For the particle in a sphere, this would, again, we have the condition that r at the radius equal to 0. And in 3 dimensions, you get spherical Bessel functions. I don't know what those mean, but there's a set of functions which satisfy the differential equation with the separation variable. It's an eigenvalue problem. And you have this condition on it, and that's how you can get a solution. This part is a little bit more involved. Okay. So I'm just going to show you what these solutions look like. We're going to study them a little bit more than this, but I just want to show you where it goes. Let's see. See, actually, let me mute that. Turn the lights back on. Okay, so when we have these two angular functions combined. This one goes like e to the I and phi. This one is more complicated. It's a function of theta. For this one, there is that quantum number m. Which so far it just has to be an integer. We don't have any other restrictions. But when we solve this differential equation, we find there's another quantum number, L. And these solutions for L can be any integer starting with 0. But then m is restricted. So for some value L, n takes on the range from minus L to plus L. All the integers from minus L to plus L. How many are there? Well, there are 2L plus 1. So let me write the table now. So we'll write down L and M, the number of N's, and then the common name, or better yet, spectroscopic name. Okay, so the first value of L could be 0. M ranges from negative L to plus L. So what are the values for M? 0. How many do we have? Just one. L could be 1. That's the next value of L. What are the allowed values of M? How many are there? 3. Next value of L is 2. 2L plus 1 values of M. So they're 5. Next value is 3. 7. Okay.
This needs to be not M's.
Say again.
Well, that's the number of M's.
Number of M's. Number of M's. Number of states at each value of L. Okay. So let me show you these pictures then. These are pictures of the rate of the angular part. It's written in a funny way because it's kind of hard to draw three-dimensional things. So in this picture, what you're seeing is the magnitude of the angular part plotted as the distance from the origin. A little funny, right? You're wanting to plot something as a function of an angle. So what he's plotting here is the magnitude of the angular part of the function, but plotted as the radius. So that first one is just a sphere. That means that the angular part doesn't change. You go over the sphere and the angular part remains the same. Here are 2 of them for m equals 0 and then m is equal to plus or minus 1. So the m equals 0 has 2 lobes. That means it's got definite, it has more probability to be at the top, at the North Pole or the South Pole. M is plus or minus 1, it's a torus, it's around the equator. More probability to be around the equator than on the poles. Here's L equals 2. M equals 0. All right, it's got lobes, but it's also got something around the waist. Here's the M is equal to plus or minus 1, looks like this. M equals plus or minus 2, another donut looking thing. Start to recognize these at all? Yeah.
All right, so are the typical like electron orbitals, are those?
That's what these
Probability
look like. These are electron orbitals, yeah. Right, exactly. So the common name for the top one is S, or the spectroscopic name, P, G, F. Remember that from the chemistry class? These names come from the old days when we were studying the spectrum of hydrogen atoms, the hydrogen spectrum. And they would try to make sense out of these lines by connecting them to and giving them names. I think this was principal. Got what this was. This was diffuse. They were characterizing these lines that they were seeing. Now, what they realized as the quantum theory is going along is that each line corresponds to a transition from one state to another. So there's 2 states involved in these things, but they recognized that they could just by they could calculate the frequencies without knowing what was going on by taking differences of numbers. Okay, so that'll come back. But anyway, this is where the orbitals, the electron orbitals, come from. They're pure modes of a particle in the sphere or a particle in the hydrogen atom. Yeah.
Sharp, principal, diffuse,
Sharp.
fundamental.
Thank you. Sharp, principal, diffuse, fundamental.
That's what Google said.
Okay. Okay, these are descriptive, they're not really explanatory, right? You're just kind of describing something, trying to make some kind of sense out of this array of discrete lines that we see in the hydrogen spectrum. But now we're starting to make some headway here in understanding what these things are about. Yeah.
So that's the probability. That's the probability.
It's the probability taking out the radial parts, just the angular part of the probability. So I take this, I have theta function of theta, phi function of phi squared. That. And then plot that in that funny way. Function of theta and phi. So the radius of that is this. It's kind of an awkward plot. I haven't found a better way to plot it, but this is the common way to plot it. Plotting just the angular part. It's not the orbitals themselves, it's the angular part of the orbitals. But this is the way it's commonly presented.
So it's the probability of finding the particle.
On the surface of the sphere at some radius. So you fix it at some radius. And this will be the probability of finding a particle at that angle, at those two angles, on the latitude and longitude of the sphere. But then plotting the radius distance from the origin is this probability. So that S function, for example, at the top, it's a sphere, it just means that it's equally likely to be everywhere. This one is more likely to be at the north and south poles. Things like that. So Mr. Silva had his hand up first. No, got it.
So it's just the probability density for the angles.
Yeah. Okay. Yeah. Yeah. So the radius of this plot is this, and this is what is being plotted there. Kind of weird, kind of an awkward way to do it. I keep thinking I can find a better way, but this is the way everybody plots it. So
For like, this might be more chemistry, but if you get to like bigger and smaller atoms,
yeah,
does that stretch or compress
yeah.
the?
Well, that's you're talking about the radial part, and that's the problem with plotting it this way is you're confusing it with the radial part of the wave function. That's why I think there's got to be a better way to plot it. Yeah.
For fixed radius.
Yes. Okay. Yeah. For a fixed radius from the center, then plotting it as a function of angle, and what we're plotting is not the radius, it's the magnitude of the probability in that direction. Not plot, but what I'm hoping to do is that this looks familiar, although you've never understood where it came from. Now you're starting to understand where it comes from. So that's why I'm showing this, and why you have it in the book, because it touches what you've seen before. Yeah.
So the radius you would want to choose would depend on the atom.
Yeah, well, it would be true for any radius. If you're to fill out the total probability, you're going to multiply by the square of the radial function. So there's a radial dependence to the density that's not shown here.
So if you were going to do that, you would like give it some color grading or something.
Yeah, you could do that, right? Yeah. How do you plot a three-dimensional function? Yeah, it's a little tricky, and this is not just a three-dimensional function. You really want to get the phases of these things in here. These are complex numbers. This plot doesn't tell you everything about these functions, but we're taking the magnitude squared. So it's a challenge to try to draw these things in a way that's easy to understand. There's a lot to try to show. Okay, so your homework is going to be to look at these functions. He's going to show you these functions. They're laid out on page 166. I'll write them down here for you so you can see. Send this away.
Does that mean it has a probability of finding it if the origin is 0?
No. See, that's the problem. With this plot is it's telling you something that's not right. Probability is not at the origin. The probability is 0 at some distance from the origin, depending on the angle. That's the problem with this plot.
I see why.
Yeah, it's hard to plot.
You almost need like 3 plots.
Yeah.
All we have 4 dimensions.
And the problem is you want these things to be kind of give you some intuition, and it's difficult because the functions are in 3 dimensions, so it's starting to be difficult. And these are complex functions. It's a little hard. I haven't found a better way to do it yet, but I still think it must be. Okay, so I'm going to write down these functions for you. They correspond to these. So these functions are called YLM, the product of theta. Oh. So we have 2 quantum numbers because we have the 2 angles. And the quantum number L corresponds to S, P, D, or F. That is 0, 1, 2, or 3. And the quantum number M has some range which is determined by L. So the first one here is Y00. That's just a constant. I'm not going to write down the constants because it'll take me all day to write all the constants. So there's some normalization function. If you want to normalize this so if you integrate over the sphere, the total probability at that over the sphere is 1. So that's what these normalization constants are going to be here. Okay, then L equals 1. So this is L equals 0, M equals 0. L is equal to 1. Let's try the M equals 0. This Y10 is a constant times cosine theta. Right, the n is equal to 0, so there's no e to the im5. That's just a constant. Do plus or minus 1.
Does Y11 equal Y1 negative 1?
No,
Um,
they're complex conjugates of each other. Almost. That's not exactly true. No, that's not exactly true. It's on page 166. So I'm just going over, you're going to look at it again in your homework. So there's constant out front. I'm not going to write down the constants. Okay, and it goes on. It goes on without limit. For the particle in a sphere, there's no limit because the particle is surrounded by an infinitely hard potential. And so there are an infinite number of these states. Okay, so I want to point out here that the angular part is independent of whether we're doing a particle in the sphere or the hydrogen atom. Or we could do a 3-dimensional simple harmonic oscillator. That would be another version. The angular part is going to be the same in all cases. So this angular part comes about for So the angular part is the same. And the reason for that, I'll go over next time. There's an operator associated with the angular momentum. So that what will help you to understand this is for us to go look at the angular momentum operator. Which is form a cross product of R with P, where P is now derivative operator. P minus I H bar times the gradient operator. Review of the gradient operator. Let's write it down for you. Gradient in 3 dimensions is like a 3-dimensional derivative. Called gradient. Fusion coordinates looks like this. Here's a version for the spherical coordinates. And again, that's in that appendix 5 in the back. If you're interested, let's see. I don't know if it helps to write it down, but there's a version for this spherical coordinates. And so this is the operator we're going to be studying next. And this will tell us more about why these angular momentum states, eigenstates, come out the way they do. Yes, sir.
Is there a hat on top of that L?
Yeah, it's a hat, it's a vector, but it's a vector operator. Just like P should have a hat over it. So if I want to extract the angular momentum from the wave function, which would correspond to the values that could be measured in an ensemble measure, then I would use the L operator. So then I integrate over the volume, 3-dimensional. Corresponds to the ensemble average of the angular momentum. And there's some interesting subtleties involved in this that will bring us back to commutator relations. We're going to say there's a commutator of this angular momentum operator with various other operators that we have in the problem. That will be the last part.
So is that vector R also R hat or
Yeah,
vector R hat?
right. Remember that R, you could write R as just a number. If the wave function is a function of R, you could write R or as an operator. It just means the coordinate that's in the wave function. So you can either write it as just R or as an operator, which is just gives back the vector one. So we were writing X hat, P hat. This P is in the X direction. So now if we look at the commutator of L itself, for example, we're going to have commutation relations between X's and P's and all that stuff. So that we're going to get to there. Okay, so this is a lot at the end. I'm trying to touch it, get it to the point where you can at least make contact with things that you've seen before without much explanation. And they were descriptive, but not being explanatory. So I'm hoping that now you'll have a deeper explanation of these pieces. They're coming. Yeah, Rob.
So what's the Y itself? Is that that's part of that's like it says up there, that's part of the given angle. Right, that's the angle.
The wave function will be radial part times the y of it. And we have the radial part depends on which of these problems you're looking at. The radial part will be different, whether it's for particle sphere or a simple harmonic oscillator or hydrogen. We'll have a different radial part, but the angular part will be the same. And that's because of the spherical symmetry. There's an underlying reason for all of this, which has to do with symmetry. Symmetry shows up. If you have a problem like a planet going around the sun, moving in a spherically symmetric potential. That's going to show up in the nature of the motion of planets. Symmetry of these problems, spherical symmetry is the same symmetry. Again, in quantum mechanics, it shows up in terms of the angular functions that constitute wave functions. So this is all underlying all of this is symmetry, which we haven't studied much of. But the study of symmetry is very helpful in all of this. In quantum mechanics or in classical mechanics, understanding the symmetry of the problem and how it shows up in the solutions. We're not going into that, but it's a very elegant subject. I hope you get to see it. Any other questions?